Good. So welcome back, everyone. So now we will finally start with computer graphics. First, a few final organizational marks. Some questions came up in the break. A couple of people had problems subscribing to the course because the system said that the course is full. There should not be a space limit for this course, so this shouldn't happen. You should be able to register till I think April 29 is when it closes. I sent an email to the Osiris people yesterday to fix that or to check that, and I will drop by there today, so I hope they will fix it. So if you haven't subscribed to the course, try it again tomorrow. If that doesn't work, tell me on Thursday, and then I will see that we can get this going. Good. For the practicals, I forgot to mention this. If you're not a game technology student, if you didn't follow the game programmeren course in the first period, you Arya wrote a nice script about that. If you have a Java background, go to the website of that course. Under, I think, literature, there is this script of the course. If you browse that, that gives you a good start. That worked for the teaching assistants who didn't have an XNA background either, an C# background either. They looked at the script and they were able to adapt quite easily. So that should work out for most of you. I forgot to mention that there is this script. Then there was this other thing at AS Quadrat. I heard they announced the book as optional. Yeah, I mean, it is optional insofar as I do not say, okay, read this, and that chapter. I will not talk about this in the course, but you have to read it and know it for the exam. In that way, it is not mandatory to have the book. You can pass the course by just following the lectures and the tutorials. But of course, since I will stay very close to the book most of the cases, it is quite of an advantage for you to have it. So I strongly recommend that you get the book, but of course it is not really mandatory to have it. Good. All right, so let's finally start with computer graphics, and now I finally show some computer graphics video. All right, so this is just a little appetizer as a start. So let's check if that works. Yeah. So the rest of today's course, I will just give a short introduction into what computer graphics is, and then a little bit about the basic methods to just give you an overview, and then in the following lectures we will go more into the details. Good. So yeah, computer graphics, we all know computer graphics. For example, one of the things that often comes first into your mind when you hear computer graphics is computer animated movies, but and also like if you turn on your computer, you have a graphical user interface. So computer graphics is ubiquitous, but what is it exactly that we are studying when we say we want to study computer graphics as part of a computer science curriculum? And if you look at the book, what the book says about computer graphics, it says computer graphics describes any use of computers to create or manipulate images. And the important part here is this create images, so not that much the manipulation. So basically, when we talk about computer graphics in computer science, we mean we create an image of some virtual world that contains some graphical objects from a specific view. So we create a realistic image of a virtual world. Of course, if it is a virtual world with virtual characters like strange bunnies or so, it is not realistic, but it looks realistic in a way that, for example, the fur on the bunny is rendered in a way or is presented, shown in a way that looks realistic. And of course, this is a rather vague definition of it, and there are a lot of other disciplines of computer science that are related to it and that overlap. So, for example, other disciplines that often are mentioned in this context is image processing and computer vision. So, I just want to let you know a little bit about these areas so you can get a better idea about how it fits in. And what we really mean when we talk about computer graphics, because like everything that you have on your computer is some sort of a graphic. But for example, there is also image processing, which is basically takes an image as an input and performs some action on it. So image compression falls under this. Also, if you take a photo with your digital camera and do some noise reduction, some sharpening of the edges, or for example, Robbie Tan, one of teaching assistants, is doing research in image processing where he has images with fog and he tries to automatically remove the fog, which can be used, for example, when you have a driving application and it's foggy, then you can see the signs better by removing the fog automatically in your image with image processing. So this is the area of image processing, which is not what we usually deal with in computer graphic. Another area that is related but different from computer graphic is computer vision. There is also a lecture given by Robbie Tan about computer vision. In computer vision, we try to get an understanding from an image of the real world. So we take an image, for example, with our digital camera, and then we try to recognize objects. So for example, if there is a bunny in this object, I try to recognize that there is a bunny, that it is at this position in the 3D world in this based on my 2D image. So this is what we do in computer vision. And computer graphics, we basically do the opposite of it. We have an idea of a virtual world, and we want to create that virtual world, and then we want to create an image of that virtual world. So for image processing, we take an image as an input, we modify this image and have an image as an output. For computer vision, we take an image as an input and have abstract representation, some information about it as an output. For example, there is a bunny, it has this size, it is at this position. And in computer graphics, we have an abstract idea, a representation of a virtual world. For example, we want to create a wood and we want to place a bunny there. It should look this way and it should have this size. And then we create an image of it. So it's basically the opposite around. But of course, those areas all overlap. So we use techniques, for example, from image processing also for computer graphics. Techniques from computer graphics are used in computer vision. So the borders are kind of smooth, but the general idea is clear that we split it in these three different areas. Of course, there are also a lot of other related fields, like, for example, human-computer interaction, because a lot of the interfaces are based on graphics, virtual reality, information visualization. So these are all kind of things that are related to computer graphics. So I talked a lot about what is related to computer graphics and what computer graphic isn't. It is not computer vision, it's not image processing. So let's look into what computer graphics is concretely. What do we study when we study computer graphics? So I said we want to create an image of a virtual world of graphical objects from a specific view and present that image on a graphics device, which usually is a raster display. So a raster display is basically just a display with a lot of dots or pixels, and then you give the pixels a color, and then you have an image there. So what we have is we have the idea of a three-dimensional virtual world. We want to represent, and then we want to create an image as if you were to look into that world and then take an image with your camera. And so this is basically the process. We have to create this virtual world, and then we have to use this virtual world to create a two-dimensional image of it. And the technical terms that I use for this are called modeling and rendering. Modeling is basically a mathematical specification. So the modeling is basically creating a description of a 3D world or a 3D scene in a language that a computer can understand, which basically means some mathematical specification. And Then we describe the 3D scene as a 2D image on a computer screen, which is a raster display, so basically a matrix of pixels or single dots. So yeah, but when we describe this scene, we usually it's of course easier to deal with an abstract representation of it than dealing with single pixels. So for example, if you draw if your world has a circle, you can uniquely define a circle by a center, and by a radius. So by just two numbers, a radius and the position, the center of the circle, you can uniquely define a circle in your three-dimensional world. So you just need two numbers. Whereas if you operate on the pixel level, you need to store every single pixel here that is on this circle here. And of course, that makes it more difficult to manipulate it, to make it larger, to scale it, to change the color and things like that. So this is why we're dealing with this abstract representation in the modeling step. But then we have to somehow put this abstract representation onto the 2D pixels on the screen. And this is basically what we call the rendering process. So rendering is basically bringing this 3D model, this abstract description on the actual screen. So make the transition from the 3D description to the 2D pixels. And rendering is a general term that is often used if you make the transition from an abstract description to a concrete pixel representation. So for example, also your web browser Firefox has a rendering engine because it translates the abstract HTML code into concrete pixels in your browser window. But in graphics, if we talk about rendering, we usually mean that we take the 3D representation of an object and create a 2D bitmap. And that includes, of course, the projection of the 3D scene. So you have a 3D scene and you want to show that on a 2D screen. So you have to project the 3D model from a 3D world to a 2D world. And it includes the process of putting color on those objects, considering light, considering surface and all this. So this process is, the rendering is usually the projection from 3D to 2D, and what is called shading. And shading basically summarizes all kind of activities involved in putting texture, putting light, putting colors, putting shadows on the image to make them look more realistic. So there is a simple example here. We have the modeling, which is basically a mathematical description of an object. So you see here, this is, I don't know if it's a mouse or whatever. And this is described by, oh, no, you don't see it. Yeah, but if you download the slides later, you see that this is a description with simple polygons, triangles, squares to describe this three-dimensional creature here. And then you put some color on it and you put some texture in it, consider the lighting, and then you get a more or less realistic image. And this process then of the lighting is called shading. And the other thing is the modeling, and then the transition from the 3D to the 2D model is the projection. Another thing we deal often with in graphics is, of course, animation. You already saw this little clip with this mouse here, but the animation will not be covered in this course. Also, we will not do much about modeling. We will only cover basic geometric objects, circles, lines, planes, and so on. But we will not talk in detail about how to create those models, but we will talk a lot about how to make those models, if we have them, how to make them look realistic. Good. Yeah, so that's what we do in computer graphics. Now the other question is, why do we do this? Of course, you already saw the movie, and I already said that movie industry is a big driving force of computer graphics, not just animated movies, but basically all movies that you see, almost all movies that you see today in the movie theater have some sort of CGI. CGI is a term for computer generated imagery, which is some sort of special effect, sometimes not even noticed, but there do some graphical modifications on the images to create certain effects. Virtual reality is another application where graphics are obviously used. Games is a big area, like now this year we have the Game Bachelor, so I don't need to motivate why games are relevant and important. But for the other part, I mean, the game industry is a huge market. It is bigger now than the movie industry, as far as I know. So the games is really a driving force also for computer graphics, that they always want to have faster and better graphics. So these are more the kind of the leisure applications, and these are more the kind of the serious applications. Of course, the transition from a game and virtual reality to simulation is pretty smooth, and but of course, you can use simulation not only for gamings but also for serious applications like serious gaming, firefighter training, flight simulation, car simulation, and that is also a huge application field, of course, for computer graphics design, computer-aided design, architectural design is also big, very much related to computer graphic, medical imaging. So these are the more serious applications. At the top, we have the more leisure applications. Information visualization is also some sort of a serious application, but I put it separate here because information visualization is also, it's not always considered as an application, it's sometimes also considered as a separate field, so not necessarily an application of computer graphics, but like a field like computer graphics, but of course they use a lot of computer graphics as well. So, but important in that context is to know that in computer graphics, we're dealing with the computational aspects and not with like the aesthetics or image composition. So we want to make realistic images and want to know how to do to make what we have to do to create realistic images, but we don't necessarily need to create nice images, so we don't really look into aesthetics or image composition here. And information visualization is basically the area that deals with how to represent data to get better insight or better information about it. And of course, computer graphics is used a lot there. And another area is, of course, a lot interfaces, human-computer interaction. And again, here the transition to again, here computer graphics is very often used in interaction, but again, also this overlaps a lot with other areas. So, for example, you probably all know the Microsoft Kinect system, where you can move in front of your screen and then it tracks your movements. So that is basically a computer vision problem, that you need to recognize the person and track the person's movements. But then this person's movements are usually or sometimes displayed on the screen in some sort of an avatar, and that would then be the transition to the computer graphic. So the computer graphic takes these movements and then creates a realistically moving avatar that is a representation of you. That is then the computer graphics part of it. So you see these areas all overlap a little bit, but I think it's kind of nice at the beginning when you start learning about computer graphics to see a little bit how it fits into the general field and how it is related to other areas. Good. All right, so let's get a little more concrete what we want to do here. So if you look at how computer graphics is usually taught at universities, there are basically two major ideas or philosophies in how to teach that. So, so this is the one is the more theoretical basics and background, and the other is the more practical, the applications and the libraries. So basically the application libraries deal with questions like, okay, what kind of function do I need to draw a line, versus the theoretical approach usually deals more with how does a function how does the function that draws a line calculate the pixels? When I give him one pixel and another pixel, how does it calculate the pixels in between? So this is more the background. And here at this university and in this lecture, we will follow more the first approach. So we'll look more into the theory, into the background. So this is not a programming class about computer graphics. You will do some programming in the practical, so you will learn a little bit about it, but the major focus of this course is more about the theory, about the background, and there's one reason for this is that people sometimes argue it's better to teach the background because the background doesn't really change that much, whereas the practical, if you learn like OpenGL programming, then the API of OpenGL changes, and then it is easier to learn a new API or to switch to another API if you have a solid theoretical background, whereas if you learn an API, then switching to another one sometimes is more difficult. That's one of the arguments and one of the reasons why people sometimes say it's better to teach more the theory than the practice. of course, there are also other opinions about that. And it also has disadvantages to learn more the theory than the practice. And the other thing is, this is a little like a unique here at Utrecht in our program, that we follow the philosophy that we teach also basic knowledge from the theory side as part of the courses and not as separate parts. So, for example, you don't. When I studied computer science, I had 3 pure mathematics lectures that we had to follow, and this is not the case here. But here we have the philosophy that we teach the theory and the backgrounds that you know as part of more applied courses like computer graphics. So we will do a lot of mathematics here that you probably a lot of the mathematics that we do here you will need for the graphics programming, but we might also do a couple of mathematics things that you do not really need on a day-to-day basis as a graphics programmer. But the idea is to use the graphics course also to teach you some mathematics, which has the advantage that you see already when you learn the mathematics how it is applied and why you learn that. So, for example, in my case, we had the first 2 years we had a lot of mathematics courses, and we were learning all this mathematics, but I had no clue why I'm learning this. And then like 2 years later, I had a course where suddenly we needed some of the stuff we learned in the first year in the mathematics course. And then I was like, oh yeah, that's why I was supposed to learn that. And here it is more practical, so hopefully that makes it also a little easier. There are, of course, also disadvantages with this approach. One of the major drawbacks with this is that it turns out that people who learn the mathematics in relation to a concrete application sometimes have problems generalizing then to other applications. So you learn the mathematics with a graphics background or graphics context, and then you have to use it somewhere else, and then you have difficulties using it in that other field because you're too much in this graphics related thinking. So I'm telling you this also to explain when sometimes in a lecture I will go into more mathematics stuff and you don't see a concrete connection. That is then basically to teach you also more about the mathematics, which is also a goal of this course. And also I will also for you to make sure that you are aware of what we expect you to learn from this course. Good. Yeah. So there will be a lot of things that we do not do. We'll only talk a little bit about graphics hardware in relation to the practicals. We will not talk, like I said, about 3D modeling. There is a separate course for this, Three-Dimensional Modellieren, which is taught by Roby Tan. It's a bachelor and a master course, so you can do this already at the bachelor level or later at the master level. Animation, we also not cover animation, but there is also a course about animation. It used to be a seminar, so as far as I know, starting next year, this will be a course. A lecture, but it will be on a master level, and we will not talk about interfaces, but there will also be a course about interaction technology as part of the gaming bachelor. Yeah, good. So just a few more general comments because we have this special situation with this course here. This course is a little strange or weird in a way that we have a huge amount of people, not only number-wise, but also with very different backgrounds. So there is always the situation that we have a couple of people here who have no clue at all, who are very unexperienced, and then we have the other extremes, which are the cracks and the graphics hackers. I would not be surprised if we have a few people here who probably know more about graphics than I do, at least about the practical part. And it is very difficult to find a good balance in this course. So when I look at the evaluations afterwards, there are always people complaining, yeah, this course was too easy, it was too high level. Geen diepgang is something that you often find. So if you're one of those cracks here who will be disappointed by the course, I'm sorry, but there is not much I can do because it is an introduction course, and I have to be aware that there are not much people who have experience in this, and for them it is a lot of material and is a lot of new stuff. So we have to find a good balance. So if you are one of those experienced students who are not who want to be challenged more, just be happy that you have a course where you can get a good grade without much effort and put your effort into your other courses. That's the recommendation I can give. Sorry if you're disappointed of it. Yeah, for the other extreme, of course, there are people like this year we have this extreme that we do C sharp. We basically assume that you have the programming level that you have after taking the first year course of Introductory Game Programmieren, I think it is, from Arjan. But as I said, if you have a Java background and look at the script from Arjan, you should have no difficulties making a transition. If you have programming difficulties, go to the teaching assistants and ask them. They can help you or give you pointers where you can find information. So that usually works out. Good. Yeah. All right. So, here. Good. Yeah. So, so we'll not talk about this modeling in detail. We'll not talk about animation. Not talk about interface, but we will talk a little bit about modeling. So the basics, the basic shapes, and we will talk a lot about rendering. So. I put this in quotation marks because it's not a really specific definition, but you can think about modeling is basically the process of creating a 3D world, and rendering is the process of creating 2D images based on these 3D world or 3D models. And there are two basic approaches to do this, which I will roughly introduce today, and then later in the lecture we'll go more into detail with it. One of them is projective methods, which will be the most part of the lecture, and the other part is ray tracing. Good, so let's start with projective methods. So the idea of a projective method is that we create a model of our three-dimensional world. So in this case, it is a very simple world and a very simple model. So we have our three-dimensional world. We have a three-dimensional space, and in that space we create our model, which is in this case just a triangle. So we use 3 points to define a triangle. Or, yeah, not surprisingly, 3 points can be used to define a triangle. Then we need to define a color of the triangle. We need to define, of course, the position where it is in a 3D space by specifying those 3D points. And then we have our 3D model, in this case a very simple one. If you saw the mouse, it was a more complex model, of course. We'd had, I don't know, thousands of triangles probably. And now we want to bring this 3D model onto a 2D screen. So we say we have a 3D world, and then we assume we have a position here where the observer is. So this is supposed to be an eye. Yeah, my drawing skills are also something that is often mentioned in the evaluations, but yeah, I'm a computer scientist, not an artist. Good, so we have a person sitting there in front of the computer, and then we have the computer screen, and then we're looking into this virtual world through our computer screen. So we basically need to create a 2D image of the 3D world on this screen. And we do this by projecting this image, this world, onto the screen. Here in this world we just have one object, so we just have to project this triangle onto the screen. So what we do is we take those corner points, project them to the pixels where they go through on the screen, and then we know the 3D model in the 2D space. Since we know that it is a triangle, we can connect those points, and then we can put the color on them, and then we can do some other light processing. Like I said, this is called shading, and then we have our 2D image of that. So this is basically the idea of it, with a very simple case with just one triangle. Of course, we can have more. So interesting question is, of course, what happens if we have two triangles that overlap each other or that are in front of each other? What do you have to do then when you do the projection? Any idea? Yeah. Yeah, exactly. So when we do the projection, we have to consider the order of the drawing. We can either draw from the back to the front. So if we draw the objects from back to the front ones will be drawn over the ones on the back, so they will always appear in front. or we have to do some check first about the order and then only draw the objects or the pixel from the object that is in front at that position. Right. So you see there are a lot of other things involved that we need to do when we do the projection. We will talk during the lecture about how to do the projection and what kind of things are involved that we have to do here. Good. And yeah, this is very often used to create graphics, especially in games, because this is very fast, and this is what you do when you use OpenGL or DirectX, which are graphics APIs that can be used to program graphics, and they are supported by the hardware, which is why they're fast, which is why they're used in games. And we will do this year in the practicals. And this is in contrast to the other approach, which is called ray tracing, which is creates more realistic results, but is on the positive side, but on the negative side is much slower. The idea of ray tracing is basically just the other way around. For the projection, you look at the model and you project it on the screen. And for the ray tracing, you go from the observer and you say, okay, I'm looking at this scene. So I basically shoot a ray from where I'm looking to the scene, and then I draw what I see on the scene. So for example, if you have here, oops, where's my pointer here? If you have here another object and you want to know what do I have to draw in this pixel to create an image of that scene. So here is again my observer. Then you shoot a ray through that pixel and then you continue on that ray till you hit the first object. And then you know, okay, I have to draw this object here. So if this is, for example, a red triangle, you have to put a red pixel here. And but of course, we also have in reality, when we look at realistic images, we do not only like. If you take, for example, a red ball and you put it here, or you put it outside, or you put it somewhere else, it always looks a little bit different because you have influences from your environment. Like you have light here in this room, it's very dark, outside it's very light. So a red ball looks different here than it looks somewhere else. If I take this ball and move around it, it also looks different, for example, because of how the light reflects. Also, a red ball that is made of plastic looks different than a ball that is made out of a red ball that is painted, that is made out of wood and painted. So the material also looks different, and especially the lighting is something that really depends on other objects, because first of all we have a light source that reflects the light and that influences how I see it, but also objects reflect light. So if I open the window here, the light comes here, it is reflected, and it changes also how the light situation is in the back of this room. And for example, if I have a lot of red objects here and the light comes here, that also changes how people perceive the light color here. So all these lights, these objects and everything that we have in our virtual world or in our real world influences how we see the light and the color on one particular point, which is why here in ray tracing we do recursion. So we calculate the shading based on we basically follow this ray and see how the light what kind of influences the light here. So if we come to this point, then we say, okay, this is if we have a light source here, like this is supposed to be a lamp. So then we say this is reflected here. So we see here we have a light source that influences the color here, and that influences how I see this point here from this position. If I would do the modeling from over here, of course, that changes again, because then I have a different reflection vector. So these are all the kind of things that we want to look into it, but later. So don't worry if you don't really understand it now. But the idea is basically the idea you should understand is that you recursively look into how the different objects are influencing the light on this particular point that goes into this particular pixel, which is why ray tracing produces much more realistic images usually than these projective approaches, because the ray tracing considers this recursive dependencies, but because we have recursion, it always takes very long to calculate them, because in theory every object in our virtual world can influence the color on one particular point. So we have to, for each pixel, we have to go through every object, whereas in the projective method we look at the objects and project them on the screen, so we only have to go through each object. Good. Yeah. So this is why basically is summarized here. It considers the global illumination by considering all influences, why it creates more realistic images, but it is therefore also traditionally very slow. Good. And last year in the practicals, they had to implement a ray tracer. So this is not from the practicals. These are just examples from ray tracing. So you see you can create very realistic images with it. But of course, calculating those images takes a lot of time. And these are some of the examples that they did last year in the practicals, in the ray tracing, where they wrote a ray tracer. This year we'll do shader programming, so you will have different images here, but I hope that in the end, or that next year, I can also show some nice images that you did in the practicals. Good, yeah. So in the practicals, we will focus on projective methods, and if you deal with projective methods, a term that is often mentioned is the so-called graphics pipeline. So in the remainder of today, I will just give you a quick overview of the graphic pipeline. So this is probably some of you will get lost about this or not understand everything in detail, because I'm just scratching it basically to give you a little understanding of the terminologies and the steps that are involved. And then during the course of the lecture, we'll go into the details of everything, but you need to get a high-level overview first to also be able then to do the practicals. Good. So if we speak of a 3D graphics pipeline, we basically you often hear the term graphics pipeline in relation to computer graphics, and there are different interpretations of it. And the term is used in a different context. For example, there are really hardware pipelines. There are also pipelines that are implemented in software, and also the term pipeline is sometimes just used to explain a high-level concept of it. But what they all have in common is the idea of a pipeline. This is a general term that is used in computer science, also a lot in parallel processing. In computer science, we always speak of a pipeline when we have a process where we have certain steps, and each output of one step is the input for the next step. So, and that is why it's often used in parallel processing, because if the input of the next step is only dependent on the output of the previous step, then you can, of course, do the steps in parallel, because if one step is finished and you can send it to the next processor, and the original processor then does the step with the next piece of data, which is also why it's of course used a lot in graphics, because speed is, especially if you want to have real-time graphics, very important. Good. So graphics pipeline, if for example, if you look at the book, these are just two definition or two descriptions of graphics pipeline that I have from the book. First at the high-level introduction, and the second one is from the chapter about 3D graphics pipeline. And one says it's a special hardware or software subsystem that efficiently draws 3D primitives in perspective. And then the second time they say it's a sequence of operations transforming 3D models into pixels on the screen. So you see those two rather vague descriptions of it that are kind of a little vague, but the basic idea is basically, when we talk about the pipeline, a pipeline is basically describes the way from the 3D model to the 2D pixels. And so let's go through the steps that we usually do when we do this. So when we do graphics programming, we have an application. This application computes a 3D geometry, our 3D model, and then makes calls to a graphics API. So API stands for Application Program Interface. Just for curiosity, who of you is when I say application program interface, who is not familiar with these terms? For whom is this completely new, or who does not know immediately what an API is? Okay, good. And who is the other extreme? Who is finds it kind of ridiculous that I explain what an API is? Okay, good. Yeah, so these are the cracks. So yeah, just to also for you to understand that we have this sometimes when I go into details or sometimes when I'm not detailed enough, it is kind of difficult to find the balance with this course. But of course, if you're lost at any time or so, just let me know. I try to make it understandable. But usually, like the people who don't have an understanding, it's a lot at the beginning. But if you keep track with the course and if you follow the practicals, then after a while you get familiar with these words. So and then it comes in quite easy. So an API is basically some sort of a library or a set of functions that is used for some thing, special functions, and of course in our case it's graphics. So if you want to program graphics, you usually use a graphics API, which are a certain set of functions that help you easily create nice graphics images. And in graphics we often have API that are OpenGL is a very common one, or the Microsoft version is a Direct X or Direct 3D is the graphic part, and then we also have shader languages, which is H. Where do I have this? I wrote it down here. I know it was wrong. It's GLSL is the shader language for OpenGL, and the language for Direct it's HLSL. So the shader language is basically the programming language that you use to program the graphics hardware, and they are based on this API, OpenGL or DirectX. So don't worry if you don't understand it now. You will hopefully after the practicals. Good. So the basic idea is when we program something in graphics, we have an API, and that API supports certain graphics functions, and it also supports certain geometry that we deal with, and this is usually called primitives. Of course, from a mathematical point of view, we can create all kinds of models. We can create spheres, triangles, polygons, splines, and curves. But the graphics usually supports only a subset of these, and these are usually called primitives. And one of the most common primitives in graphics is a triangle, because with a triangle we can basically describe almost everything. You can even describe a circle with a triangle if you make the triangles small enough. So this should look like a circle. Now if you make small triangles here, so if you make large triangles, you will end up getting a circle, or not a circle, but it will be obvious that this is not a circle. But if you take a lot of triangles, the difference here will be so small that you cannot recognize it with your eye, and then you see it like a real circle. This is why a triangle is very often used, because you can create a lot of things with it, and the processing of it is quite easy, as we will see later. Good. So the API, the application creates these models and then sends it to the graphics pipeline, which can be a software or a hardware implementation, which can be hardware or a software implementation. And then the graphics pipeline does the so-called vertex processing, which is basically the transformation of the 3D to the 2D. So this is what I explained earlier as this projection. So it basically takes the vertices. So in this case, a triangle, you have 3 vertices defined by these 3 points here. You project them on the screen, and then you have a 2D representation of the 3D triangle on the screen, and this is done in this vertex processing step. There are, of course, other things done in this step. So for example, you can do some first shading there, you can put color there, do some color processing. Another thing that is done is called a process called clipping. So for example, if we look at the screen, we can only see a small part of our virtual world, of course. That is defined here by the size of the screen. But if we have, for example, a triangle that is like this, so here it intersects with this part that we can see, so we only see a small part of it, then we have to consider this, of course, with the projection, because if we want to project it on the screen, we cannot project these 2 points, but we need to project these 2 intersection points here to know that this triangle goes here, because we cannot project these points here because our screen is too small. And this is done in a process called clipping. So this is basically cutting off this part and creating this new triangle that is then projected here correctly, so it looks correctly on the screen. So this is another thing that we want to look into, and this is all part of this vertex processing of the pipeline. So from here we basically go from a 3D model of our world, of our scene, to a 2D representation on the screen. So we transform the geometry from 3D to 2D, but we still have a geometric representation of it. We still have on our 2D space now 3 points that define a triangle with first color information probably, but still a geometric representation. But in the end we need to have single pixel. For each pixel we need to make a decision. We give it a color or we do not give it a color, and what kind of color do we give it based on that geometry. And this process of going from the geometry to the actual pixel is called rasterization. So the rasterization, so this is the step from 3D to 2D, and this is the step from 2D then to pixels or fragments. So the term fragments is usually used here. Fragment is basically it's basically a pixel, but it's a more abstract term to describe it, because at that stage we're not really dealing with pixel. For example, if we have overlapping triangles, then for each triangle we have a fragment, how this would look on the screen, but when we draw the actual pixel, only the one that is in front can be drawn, of course. Or if we, for example, have a transparent triangle first and another one here, then both of them have a fragment, which basically is how would the pixel look like if I would look directly at this triangle. But if the first one is transparent, then of course the color that you give the pixel depends on both of them, so you have to combine them or to blend them, and this is then the next step, the fragment processing and the blending. Good. And yeah. And then you're all done, and then you can draw it in the frame buffer, and the frame buffer is then what is displayed on your computer screen, and then you have your hopefully nice image on the screen. So of course, in between you have to do some shading, and as I said, you can do this already when you process the geometry, but you can also do this later in the fragment processing, depending on what kind of technology you use for the shading to consider the lighting. And so it is better to do it earlier or to do it later in the pipeline. There are other tasks like clipping I already mentioned that also have to be done in the pipeline. So we'll talk about all these. So this is just a high-level overview to give you an idea about what it is, and what what we'll cover in this course. What we will do, we will go through all the single steps and see what is involved there. But we will also, I also brought this overview here because you always hear the term graphics pipeline and rasterization when you start the programming. And as I said, that will start on Thursday. So I think it can be a little overwhelming at first because you read all these technical terms and you don't know what it is, but don't worry, after a while you get familiar with them, and then it should work out. Good. Yeah, so this is just basically a rough overview of the lecture. Be aware it is preliminary, so it might change a little bit, and the reason why it might change is that we have the new practicals this year, so I might make some changes here based on the practicals. So if I have the impression it's better to bring something first because you might need it or benefit from it in the practicals, I will do the change. But for the first couple of lectures it will pretty much stay the same. So today we have this high-level introduction. Next week on Thursday in the next lecture it will be pretty much heavy on the math side. So we'll talk a lot about vectors, curves and surfaces to describe those kind of objects that we have in our 3D world. Then we'll talk a little bit about shading, about how to put light on those and color on those objects. Then it will become again very much mathematical. We'll talk about linear algebra, basics, matrices. Then we talk about the transformation, how we can transform and change those objects, and the perspective projection, how we can do this, how we can project the 3D model on a 2D screen. And this is basically where the first exam will take place. Actually, the exam will probably take place here, but it will cover the first 5 lectures. And then here it might change a little bit. I might do the graphics pipeline a little earlier, or there might be an extra introduction from one of the teaching assistants, because at that time the practicals will start with the more concrete programming assignment. So the first assignment that you will get on Thursday will be more a tutorial that gives you a general idea and also help you setting it up for those people who don't have much experience. And then in the first part of the lecture we'll cover a lot of the mathematics, and then we will go more into the graphics related stuff in the second part of the lecture. And we'll still cover ray tracing, but I don't know if we'll do it at the end or maybe also a little bit earlier. But we'll see that, and I will announce changes on the website. Good. Yeah. Final comments. Next lecture is on Thursday, Educar Theta. Tutorial and practicals start afterwards, so no practicals on Thursday morning. We will put the assignment online around lunchtime, and then in the afternoon is the first practical. But don't forget, you need to do it in a team with 2. If you want to, you can also do it with 3. So make sure you find a partner. And again, check the website for regular updates. Are there any questions? No? Then see you all on Thursday.